Is this the stuff of nightmares for you? Hello everyone and welcome back to Atman Unlimited. Let's take a tour through the control cabinet on a Fadal VMC-15. Now this will also be applicable to other machines. They're almost all split up in a very similar manner of having a central processor, access control boards, access drive amps, etc., etc. So even if you don't have a Fadal, this video may give you a little bit of insight into how other machines operate as well. So we're going to start by doing just a general overlook of the control cabinet. That's normally the cabinet that's on the right-hand side of the machine facing out to the right. And then after that, we'll go down into the office and we'll look at some of these boards in detail. Here's the control cabinet for the Fadal CNC. Now a lot of these control cabinets are similar. This is on my VMC-15 specifically. Now I gotta handhold the camera here, so sorry if there's any bounce and jitter. But let's start at the top of the cabinet and just do a general walkthrough of what we got in here. So up at the top here, right here, that's the main power supply for all of the control electronics throughout the cabinet. Now this is just a standard AT computer power supply. The problem is these really aren't made anymore, so it's getting harder and harder to find them. But if you look at it closely, all it really is a 5-volt power supply, a 12-volt power supply, and a negative 12-volt supply. So you can easily replace this with just off-the-shelf supplies fairly easily. From there, we just have a general power distribution block. Now the machine's off, so there's no danger of voltages in here. So from there, we go down to another power distribution board, and now this board is both power distribution and it has some relays. Okay, so this board is responsible for switching on and off some of the functions, and then it also has some fuses and circuit breakers in here. So then moving over, these are going to be your AXI drives. So all the motors on all your axes, your X, your Y, your Z motors, there's going to be a card for each axis. Okay. Now these are DC drive controllers. If you have AC drive controllers, they're a little different, but they'll be located in the same spot. Now if you notice I have 4, my machine's already pre-wired for an A axis. I've been working on trying to get that up and running. So then the last piece, and this is the really important piece, and I don't have a lot of light down here. Here, let's move the light. There we go, a little bit better. So these are all the cards in the card file. Now all of these cards have a different function to control the machine, and I was able to get a complete duplicate set of cards. So then from here, let's go back into my office where we've got some more light, and we can look at each one of these cards individually and discuss how they work in unison to control the whole machine. Before we talk turkey, we need to talk safety. Now it's not safety for you, it's safety for your boards. Now what we need to talk about is something called ESD, electrostatic discharge. Now ESD is basically a miniature form of lightning. Everybody's seen lightning? Well, if you walk across your carpet in the middle of winter and then you go sit down or you touch something that's metal that's grounded, you get zapped. You hear that little pop. Well, that little pop generates a huge amount of voltage and a fair amount of instantaneous current. What happens is on the insides of the ICs, or the integrated circuits, the circuit chips, there's little tiny fine wires in there that's like the size of a human hair. Well, it blows them up. No worky, no more. We need to mitigate that risk. Now, older electronics have a pro and a con. The pro is that older electronics are more beefy. They're not as fine. They didn't have the technology to make them as small back then. However, they come at a cost too, because back then they didn't protect them against ESD. So while they're a little bit more rugged and beefy, they're also more susceptible to ESD. Newer electronics is the opposite. They're much finer, smaller, easier to be damaged by ESD. However, most chip manufacturers now incorporate ESD protection right into the chip. So, in any event, whatever electronics you work on, protection starts with the surface. If you notice, you always see me in the office on this nice blue mat. Now, I like these mats because, one, they're kind of sticky but not too sticky. They're actually nice to work on. I do a lot of work other than electronics on these mats. But these are called static mats, and you can buy these mats at a whole bunch of places. Now, what makes them special is they're actually conductive. Now, no, it's not like a wire where you can pass current through them, but what it is there's like a megohm resistance per, square inch or square meter or whatever. There's a spec for it. So what it does is it dissipates any static. You'll never get a static shock generated on one of these mats. You can rub it as much as you want, do whatever you want to it, it's not going to generate static. However, you still will. That's where this comes in. Some may recognize this, some may not. This is called an ESD bracelet. And what it is it's a bracelet with a little cord on it. This goes to ground. But it doesn't go to ground directly. It has a little bit of resistance to it so that you can't get electrocuted while wearing this. Because if you ground yourself and then touch something live, bad things happen. So they put about a 1 megohm resistor in these because, again, the goal is just to keep your charge dissipated so you can't build up a static charge. So by just having a 1 megohm resistor to ground, you can do that. So these snap in. Wear it on your wrist anytime you're touching the boards. We're good to go. Now when you're on the machine, the other end of these has a little banana jack. This also has an adapter with an alligator clip. Chomp, chomp, chomp. That can be attached to a machine ground so that you can wear this while you're working on the boards in the machine, which you should. If you don't, you can blow up your boards. By the way, you cannot buy any of these components in these boards anymore. Well, any of the major ones. When's the last time you saw a brand new 386 get made? How about a 286? Exactly. So now that we got the safety thing out of the way, let's look at our first board, which is going to be the CPU board, the central processing unit. So here we have a Fadal CPU board. Now, one other thing with ESD is you always want to transport the boards in ESD bags. Now, these bags have a similar property to them. They are conductive. So there's a little bit of conductivity to the bag so it won't build up any static and it won't shock the board. Do not transport circuit boards in any other manner, in any other way than in an ESD bag or an ESD tote. That is the #1 time that boards can get damaged is during transport. You're walking, your clothing is moving around, you might be scuffing your feet on the flooring a little bit. Okay, so always transport, store in static bags. So let's take a look at a processor board. Now this processor board is the latest processor board that Fadal made. Okay, this is a 386 based board. Now all the processor boards from Fadal have a similar thing in common. They all contain some type of CPU. Now this board is called a -5 board. So if you can see the part number on it, it's -5. There are -4 boards, which are very common. There are -3 boards, which are a little less common. There are -2 boards, which are somewhat seen. And then there's a -1 board, which are very, very rare. Now also, if we recall back to our card file, the card file had slots in it. Now with Fadal machines, each board has to go into a very specific slot. Now this board goes in slot 5. Now, why does it go in slot 5, and why don't you ever see boards in slots 1, 2, 3, 4? Well, back in Rev-2, they actually used slots 1, 2, 3, 4 for memory expansion. In the newer boards, they do memory expansion a little differently, and I'll show that in a minute. So this is a Dash 5 board. Its main brain is an Intel 386. It's the exact same processor that was put in personal computers, you know, back in what? That would be early 90s-ish. Okay? And then also this board has a couple of PROMs and EPROMs on it. And then it also has some memory. So this board has 44K of memory that can be used for programs. It also stores the backlash, tool offsets, diameter offsets, and work offsets. So that is what's on this board. Every single board has that minimum amount of memory. We also have a battery, and that battery will keep the memory alive to store your set P values, your backlash values, etc., etc. And then it also has a super cap on it. So the cap will keep the board alive in between power cycles, and then if the power is off for a long term, it uses the battery to do so. Now it's important that you store and keep somewhere safe all your set P values, because if the super cap and the battery die, poof, gone. And then you need to reconfigure the board properly so that the machine will run correctly. So then this is the processor board, and it goes in slot 5. So now what are these connectors on this processor board for? Well, these two connectors hold another board. So let's zoom out a little bit here. So what this board is this is the software board. So this is equivalent to a hard drive, but it's not really equivalent to a hard drive. What these are called EPROMs. They're not EEPROMs, they're just EPROMs. They're erasable, programmable, read-only memory. Now what makes them erasable are these little windows, and inside those windows you can actually see the silicon in there. Now having these windows exposed is very bad. You do not want those windows exposed, and here's why. The way that these chips get erased is using ultraviolet light. So you take a really bright ultraviolet source, you shine it on the chip, poof, it is wiped clean, ready for reprogramming. However, if you don't have the program, you won't be able to put it back on, and poof, your operating system is gone. Now I believe the people at FadalCNC.com can reprogram these boards. I think they have the Fadal code that you can purchase. Now it comes with a sticker with a rev on it, so this is Rev 96 1B4-3, and then you can see it's copyright of Fadal Engineering because this contains all of their software that's on the machine. Now, what you want to do if you see a board like this, you want to put some black electrical tape over each one of these little windows. Black electrical tape works really good at blocking out all the light so that these won't be erased. I'm showing it to the camera right now, and we're under incandescent lighting, which doesn't generate any ultraviolet light, so we're okay for a little bit. So we'll put some black electrical tape on those after this video. Now what this board does is where it goes here. Okay? So it sandwiches there, and it plugs in, and that is how you program the machine, and that is where the operating system resides. Right there. Now we said earlier that this board only has 44K of memory in it. That is a very small amount of memory. That's how much memory my machine currently has. If you do any type of CAM usage in CAM processing, chances are your program is going to be much larger than 44K. Very few programs will fit on this board generated by Fusion 360. So with that, now what we can do is we can upgrade the memory on these. And that's where this, I'm popping stickers off. I'll put that back on. That's where this board comes in. Now what this board is it has a little bit of a logic here, and it's got some PROMs on it again. And then what we have is we have a bunch of RAM chips. So this is how you expand the memory on these boards. Now, this is a Dash 5 board, which is really cool because this board can hold up to 16 megs of memory. This card is only a 384K expansion card, which brings our total memory up to 444K. Not bad, but you know, I'd like to try to get a hold of one of the 8 or 16 meg memory boards. I just haven't been able to find one yet for a reasonable cost. So I'm going to keep looking for those. If anybody has one, I'd be more than interested in talking to you about it. So this board then installs, almost dropped it, like so. Okay, and then you seat it into those connectors. And then the whole assembly uses that card edge connector to then plug in to your card slot. Okay. So what does the main central processor board do? Well, besides running the operating system, it runs the screen, it allows you to it takes your input, but also when you run a program on the CNC machine, what this board is doing is it's calculating a whole bunch of positional points for all of the axes. So when you have a piece of G code that says G2, which is an arc move, and then you specify the center of the arc and then the end of the arc, what this board does is it runs a whole bunch of trigonometry calculations of sines and cosines, depending on what it's doing, to generate a whole bunch of little tiny points of positions at a certain rate. I think the Fadal machines run around a kilohertz. Okay, so 1,000 times a second, it's updating where the AXI position should be. And by doing a smooth update that's consistent and deterministic in time, what it will generate is it'll generate a nice smooth arc. So this is what's actually calculating all the positional points. Now once it calculates those points, that data comes down out of the backplane and then goes to the AXI Controller Cards, which we will get to in a minute. Now let's talk about the I/O for this thing. So we need output from it of a video monitor so we know what it's doing, and then we need to input to it via the keyboard. So let's look at those boards next. Up next we have the display board. So this board is what is responsible for taking the data from the CPU board, processing it. It actually has a DPL here. It's a digital programmable logic controller. And then this also has a firmware chip on it. So you can see this chip has a sticker over the window, so this one's been protected. This is the exact same PROM chips or EEPROM chips that are used to store the OS on the main board. Then over here what we have is we got 2 RAM chips. Now this is what they call dual ported RAM, so there's actually 2 ways to read and write it. And this is typically very fast, so you'll see this a lot in video cards, even today, but today's is a lot more memory and a lot faster. Then down here is the main driver for the composite video signal. Now if you notice, these cards have an extra edge connector on them, and that edge connector is for this guy. So these cards all have to go into their very specific slots, and then this extra edge connector acts as an additional backplane to connect the processor board with the display board and the communication card. So that one is the display card. Now this card goes in slot 7. Okay, so that's why there's this little jump here. So this is 5, 6, and then I'm sorry, this is 5, 6, and then 7, and then 8. Okay, so those are the slots that this board covers, and this goes in slot 7. Slot 6 is used if you have a dual arm tool changer, which I haven't seen very many machines that have one, or if you have an option for advanced feed forward. So that would go into slot 6. So then let's look at the board in slot 8. It's the computer interface board. So then this board goes in slot 8. This is the 1030 board, and this board is responsible for communications between the main processor board, the CPU board, and the rest of the machine. So this does a lot of routing and muxing of signals from the machine into the CPU board. This board is also responsible for communicating through the RS-232. So when you're doing your DNC or you're programming your machine, all of that data is coming through this connector and through these circuits over to the CPU board. Next up, we have slots 9, 10, 11, 12, and 13. And all of these slots do the same function, just with different axes. And these are the AXI Controller Cards. Now, these cards are probably one of the most critical cards in the whole system. This is what actually closes the loop on the position of each axis. So this card is going to take the command of a position command from the main CPU board, and then it's going to read the current AXI position, and it will compare the current position with the command from the CPU, and then send a command to the motor to turn to make the command and feedback equal each other. So let's take a quick look at this card. Now right here, this is the processor for this card. Now this one is using a 186 processor. So again, this is another Intel CPU. It's a little bit older, but this is where the actual magic is happening of closing the loop. Now there's two EEPROMs on this board again, here and here, and these contain the operating system for the processor to close the loops on the AXI cards, or on the AXIs. Up here again we've got some memory, and then down here we've got a whole bunch of logic chips, and there's some other PROMs and stuff scattered on the board. Now this plugs into the backplane of the card file again, and that's where the data from the CPU comes from to tell the card what it wants the AXI position to be at. And then we've got some I/O connectors here. Now this card has a digital to analog converter on it, meaning it takes a digital word, a command from this processor, and then generates an analog signal. And then that analog signal gets output on this little white connector right here, this little 3-pin jobber. Okay, so that's the output section of the card. Now the input section is kind of neat. This is a dual purpose card. Now these EEPROMs are labeled DC-XYZ. So what that means is that this firmware can run either access X, Y, or Z, and then it's for a DC drive, which is what my machine's set up for. If you get an AC machine, you have to have AC chips firmware, not DC. So very important. Okay, so then feedback. Let's talk feedback. So these two connectors over here are where the feedback comes from. Now on a DC drive machine, they use resolvers for the position of the axes via the motor rotation. So that resolver signal comes in this connector here, and then there's an analog to digital converter, an A to D, which will then digitize that, and that's how it calculates the position of each axis. On an AC machine, this connector gets used that has this dead plug in it. This connector is for encoder feedback. So AC machines use encoder feedback, DC machines use resolver feedback. So resolver, encoder. This connector up here, this is for an extra encoder. Now you can put glass scales on a Fadal machine and then connect those glass scales here to get more accurate feedback control of the axes. And then this one up here is for a clock that gets shared between all of the control cards, so everybody is clocked at the same time. And then this one way over here, this is feedback from the axes drives for how much current is being driven into the motor. So we've got resolver, motor encoder, glass scale encoder if you have one, clock, and current feedback. So then what we do is we read the position, we bring that into the processor, we get a command from the CPU, processor figures out if you're where you want to be. If not, it sends a word over to this digital to analog converter. This generates a voltage which goes out here to the AXI drive to actually spin the motor. So this command is a velocity command. The voltage is proportional to speed. So that is an AXI card. Now, this card can control one of the three axes, X, Y, and Z, based on its firmware. Now, there's also another very important thing on this card that you have to be aware of, and that's this little guy here. Now, what this is it's just a chip carrier, but it's got a jumper on it. And that jumper tells this card which AXI it can control. Now, if you have this, so this sticker says it's set for Z. I haven't verified if that jumper is actually for Z AXI or not, but slot 9 needs to be the X-axis controller card. This jumper needs to be set up for an X controller. Slot 10 is Y, slot 11 is Z. You need to make sure this jumper matches the slot that you put this card in. Okay. Now last, this card also has some EEPROM on it. Now what's the difference between EEPROM and EPROM? EPROM, remember, is EPROM is erasable, programmable, read-only memory. EEPROM is electrical, erasable, programmable, read-only memory. The difference is that EEPROM can be erased in circuit, where EPROM needs to have the ultraviolet light process to erase it. So your AXI survey that contains your offset and gains for your ball screws are stored on these cards. So if you swap them out, you must make sure to write down your survey data and then re-input that survey data, or you'll mess up the accuracy of your machine. So very important stuff that happens on this card. These two potentiometers, I looked at the card circuitry, and I believe these are for balancing gain and offsets to get the best resolution out of the D to A converter. I haven't been able to find any documentation on how to put the machine into a test mode to be able to adjust these pots or not. So I don't know anybody that plays with these pots, and they've got varnish on them to prevent you from turning them. So I would highly advise not messing with these pots unless you can find information on how to put the machine into a test mode to output a set voltage that you can adjust these pots to. If anybody has that information, I'd be very interested in obtaining that, just so that you can then adjust these boards and possibly repair them. Again, the problem with these is, the date stamp on this chip is 1982. So, these are not made anymore. You cannot buy these anymore. So everything on this board is obsolete. You have to try to find other boards that have working chips you can, sacrifice and salvage off of. That's the problem. So that's why I bought these boards, is so that I have a complete redundant set of boards. Albeit these ones are newer, so I got a bonus out of it too. So that is the AXI Controller Card, and there are 5 of them potentially. So this board is another AXI control board. However, it is slightly different from the positional axis control cards. What this is this is the Spindle Controller board. Now, except for a -6 rev board, this one's a -4. The previous board I showed you was a -5. There's not many changes between -4 and -5 boards. They look very, very similar, and the componentry is almost identical. The -6 boards are interchangeable between AXI's controls and spindle controls, but the -5, 4, etc., etc., the older boards are not interchangeable. So the spindle card needs to go only in the spindle slot. And the reason for that is if you compare this with a -4 AXI's card, you'll find some chips on here that are either missing or populated depending on the task at hand. Also, the firmware is different. So this board uses the encoder feedback lines for the spindle encoder for the speed measurement of the spindle, And then what this board is doing, if you notice, there's no output on this board to go to the AXI amp. This board sends its signal to the spindle through another board. Now, if you have rigid tapping, you need to have this encoder hooked up, and then this firmware, this will say rigid tap on it. This board, I do not believe is a rigid tap board. So when I swap these boards out, I'm going to use my original spindle controller that has the rigid tap option. What the rigid tapping option does is it basically sets up a feedback loop that gives the spindle position to the CPU and the Z-axis control board, so that the Z-axis control board can synchronize the Z-axis depth with the rotation of the spindle. So that's how rigid tapping works. We measure this actual spindle location, and then we drive the Z-axis and slave with the spindle motor encoder so that everybody stays in sync as we screw the tap in and then back out of the part. So again, almost the same exact board as the AXI control boards, just a little tiny bit of component differences in what's populated and what's not populated, and then we have a firmware difference. Okay, so this is the spindle controller board, and this goes into slot 14. Alright, so there's two boards that I'm missing out of this set to make it a complete set, and that board goes into slot 15. And that board is a clock board. Now that board generates the clock signals that are shared between all the AXI controllers. It generates the sine and cosine sine waves that are sent to the resolvers on a DC machine. And then it also inputs the feed rate override pot from the pendant. Now the clock board is the main board that has some adjustments on it so that you can dial in your feed rate. When I go to do the actual board swap, I'll try to show that board a little bit more in detail, but I don't have one right now, and it's in the machine, and I can't disturb the machine right now, so that one's missing. The other one that's missing is slot 16, which is the M function board, and that's if you have additional M functions. That board will allow you to drive more solid state relays so that you can have more additional user M functions. Now I do have the last board, which goes into slot 17. It's orientated the same way. Now what this board is this is the mill interface board. Now the mill interface board is needed to read the keyboard on the pendant, and then it also is basically like an amplifier board to send out some higher current signals to trigger some of the solid state relays and some of the M relays, turn the coolant on and off, functions like that. So that's what this board is. Basically it's just a whole bunch of logic chips that are driver chips to go out and to read stuff. So this board's pretty basic. I don't know how many versions of this board there is. This is a -2 board, which means it's a lot older board. So mill interface board. So that's going to complete all of the boards that are in the card file. That's the brain of the machine. Now, just to recap, the CPU board is what outputs, the display and takes your inputs, and then when you're running a program, it calculates a bunch of positions. Now those positions are then sent to the AXI control boards, which then read the position of the AXIs, read the command from the CPU board, and then take an appropriate action of sending a velocity command to a drive. So now let's look at the last piece of the chain for the control system, and that is the actual motor drive. So what I have here, this is not out of a VMC 15. This is out of a larger machine. I believe this is a 1 horsepower DC motor drive. The drive cards inside the VMC 15 are very similar to this board, and they work exactly the same, except they're about 2/3 of the size of this guy because they're fractional horsepower drives. The table's not as heavy, so you don't need as big a motor on the axes as you do on a larger machine. especially if you have a linear way versus a box way machine. Box ways have a lot more drag. They require more horsepower to move fast. So what is this bad boy doing? Now, because this is a DC machine, it's going to operate a DC motor. And the reason why they use DC motors first is because DC motors are relatively easy to drive. You don't actually need to commutate or control the electrical field to actually spin the motor with a DC motor. It has brushes and a commutator internally that does that for you with, a physical commutator. An AC motor, brushless motor, does not have a commutator, so it relies on the controller to commutate the motor. So the controller and drives for an AC motor are much more complex than with a DC motor. So let's first just kind of go over the connections we have here. We have power in, so you have a DC bus in, and depending on what board this is, I don't know what voltage this runs at yet, I didn't look it up. But either on the Fadal VMC 15, the bus voltage coming in is 180 volts DC, and that's generated by rectifying 120 volts AC. You can get 180 volts DC-ish. Now if you rectify, three-phase 208, you can get that up to about 380 volts DC. So anytime you're working on this stuff, you need to be very cautious about the bus voltages. DC voltage is actually pretty nasty if you get electrocuted by it. It just clamps your muscles and you just will never let go. It's DC, so it hurts. Next to that, you've got the motor connections. Now with the DC motor, there's only 2 motor power connections, plus and minus. Brushless motor, you're going to have 3. So that's a big, easy way that you can tell the difference between the brushed DC motor and a brushless AC motor. DC motor will only have 2 power connections, AC motor will have 3. Okay. From there, we've got a couple of potentiometers. Now these are critical for adjustments, and I'll go over the adjustments in another video because I'm going to have to tune in all the drives again after I swap all these cards out. And then over here, we've got some feedback and signaling terminals. So what these do is, with a DC motor, the way that they tell how fast the motor is spinning is there's actually a tachometer on the motor. So basically it's just another little tiny motor that spins and generates a voltage rather than putting voltage in it to spin the motor. So there's a little tiny tachometer, and that provides a signal to this board to tell the board how fast that motor is truly spinning. Then there is an analog input on here, and that is the velocity command. So what this board tries to do is it controls the output voltage to the motor to make the tach signal equal the velocity command signal. Alright, so that's how this board closes its loop. It's closing a velocity loop. And then there's some feedback to the drive, the current, how much current it's currently driving into the motor. That gets fed back to the controller so it knows if it's current limiting or not. So, DC drives are pretty simple. Like I said, we take the tach input, which is just a voltage, and we take the velocity command, and we want to make those equal 0. The difference between them. We want the difference between them to be 0. So in order to do that, what we do is we have what's called an H bridge at the top here. So all of these are either going to be MOSFETs or IGBTs, depending on the current voltage levels. In these older boards, these actually might be true transistors, power transistors. In newer drives, you're going to see IGBTs and MOSFETs. So it looks like there's 1, 2, 3, 4, 5, 6, 7, 8. So they probably put 2 pairs on each leg to handle the current, and basically it makes a H bridge. It literally looks like an H with the motor in the middle. So you can take power from plus, go through the motor this way to minus, or you can take power from plus and go through the motor backwards to minus. So you can spin the motor in both directions. So that's what these power switches are doing. So based on what the error is, it will turn on one set or the other to spin the motor one way or the other. And then the way that this is controlled is it uses what's called pulse width modulation. So if we turn this switch on and off really fast, and we leave it on for a short amount of time and then turn it off for a long amount of time, what happens is the voltage output gets averaged in the motor to a lower level. So that's how, you know, we control the speed of the motor, is by adjusting that duty cycle. If we leave the switch on all the time, then full bus voltage will go to the motor and it'll spin as fast as it can. If we turn the switch on and then turn it off half the time, then half of the voltage will go to the motor and the motor will spin half of its full rated speed. So that's how this card is controlling it. And if you look carefully at this card, there's no real microprocessors on this guy. This is all done with analog circuitry and comparators and stuff. And what these pots do is they're going to control the gain of that velocity loop. Now it's very critical that you go through and adjust these pots and do what's called balance the drives out. So each drive, X, Y, and Z, need to have the exact same duplicate gain between all the drives, so that when you do a circle, you'll get a true circle. If your drives are mismatched, what you'll do is you'll end up getting a sideways ellipse. And that's what that Renishaw ball bar data will show you. It'll show you how close your drives are matched, and it will also help you adjust them and tweak them in. So then there's going to be one of these drives for each axis. So if you have a 3-axis machine, you'll have 3 of these. If you saw in the beginning, my machine has 4. That's because my machine's pre-wired for 4th axis. One last card that we'll just mention real quick. This is the Temperature Controller Card. Now if you have a chiller in your machine for the spindle and or ball screws, you will have this card, and this card can be placed in slots 1, 2, 3, or 4. The only thing that this card is doing in the card file is pulling power. So you'll notice there's only a trace at the very bottom pin and then the 2 top pins. So we're just pulling power off the back plane. All of the data and control go through this connector. Again, this is another board that there are 0 microprocessors on. This is 100% strictly analog board, and then you'll notice there's an adjustment pot here on this side. Now what this board does is it reads the RTDs or thermocouples inside the spindle, and then it will compare that to this voltage, and as your spindle starts warming up, it will send the command to turn the chiller on to keep the spindle at a set temperature. So that's the spindle thermal control card. That's going to conclude our tour and general overlook of how the control boards work and function together to operate this machine. I hope you found the video informative. As always, feel free to ask questions in the comments or send me an email. And thanks for watching. We'll see you on the next one.